Thanks for everybody coming today. Real quick, how many of you is this your first time to come? Just curious. I see a meetup every now and then, a bunch of first timers, and just curious. Everybody's been here before? Okay, awesome. Well, cool. So I was hoping for like half the people, like, yeah, this is our first time. Okay, this is great. Well, welcome back then. In that case, as you know, all about functional programming here. If anybody is interested in giving a talk on functional programming, come and find me. Either afterwards, or I'm hanging out in Slack, or if you go to the meetup site, there's a public board you can post to as well. So any topic on functional programming as a concept, a language, or technology that uses functional stuff is all interesting. You don't have to be a professional at it, so if it's something that you're just kind of using as a hobby and found something interesting or relevant to what you're doing, then feel free to share it. So. Also, we're going to probably have lightning talks coming up. So if you're not interested in doing a full hour presentation, but you would like to give a short 5, 10 minute, 15-minute talk on something much smaller scale, that'll probably be coming up soon too. So might be just thinking of ideas there. Today we have Scott Murphy that's going to be talking to us about property testing and types. It's going to be pretty exciting. I don't know how many of you have messed with those before, but that's really cool stuff, so I'll let him do that here in a minute. And Lucas is going to talk to us about StarSpace for a minute.
Thank you, Jordan. My name is Lucas Watson. I'm one of the co-founders here at StarSpace 46. I also serve on the Techlahoma board. So I want to say thank you to Techlahoma and the sponsors, mostly y'all, right, who gave money to pay for lunch and all the things that Techlahoma provides. Also, on the StarSpace side, if anybody is not a member at StarSpace 46 and wants to know about what sort of offerings we have, everything from co-working part-time to full-time to reserve desks. We still have one office open for a small office, and then meeting spaces here, whether it's in this big event space with the built-in streaming or smaller conference rooms. Come talk to me after the meeting, whether you want to be a member or maybe your company would like to use this meeting space. We have some opportunities there to let you guys use this space. There's cost involved, so don't think it's free. But we'd love to make it easy for you guys to use this space for more than just meetup groups if that's something you want to do. So that's all I got. Thanks a lot.
Staging instructions. Try and do this. Did I come back online? Yay, good deal. All right, so whenever you're doing programming, you're usually presented with some sort of way that you want your data to look. For instance, you might have some sort of product database and you're creating a view for that product database. You'd have a product, a customer perhaps, some information about each of those things. However, when you're storing that data, you might want it stored in a different way. For instance, normalized for a database. So here you have a product and then you have each of the key fields normalized across it. Lastly, you might want a nice compact representation of that data where you'd have lots of information all presented all at once. Each one of those views has an optimal way that the data is organized. One might be a nested tree, the other would be a set of individual tables, the last would be one document that's flat. Basically, what I'm here to talk about is the properties that make those things possible and how they interrelate with each other. Types are a way of talking about those kind of properties in your code and making them very, very on display. So the hope is that you're able to use these things to design programs, or at least to make them break a little bit less. Okay, so when somebody says the word properties, that can mean a lot of different things. There are two kinds of properties that I really want to talk about and focus on. First are things that define an object. So given any kind of object or expression or anything you have, properties are what you know that thing has to have in order to be that thing, right? So an address has to have a street number. An address has to have a state. Then the other way of looking at things is, what can you do with that object, or how can that object be transformed? An example there would be a product number. In the example that I have here, a product number can be used to look up a product. So that's a property that product number has, talking about how you can use it. Mostly I'm going to talk about the first, because that's really where types come in. But then we'll see talking about the second as well, and that's where things like QuickCheck and other programs come in. Okay, so Haskell has a few ways to do this. The first is type encoding, and that's constructing types. Smart constructors, this is the boundary that explains exactly how you can encode those types. QuickCheck, it's what you're going to use to check the properties between things. And type transformation, this is sort of the static level, what the compiler is going to do and check for you. And then lastly, I'm going to talk about liquid types, which is something sort of in its own category. And it's very related to QuickCheck, but a little bit different. All right. Okay, so basically you're going to see this pattern repeated over and over. The gist is, at the boundaries, you're going to use smart constructors and QuickCheck. So what are smart constructors? Smart constructors are things that build types that actually check to make sure what you have as incoming data is valid. QuickCheck is another way of validating that data. So you're going to make sure that the stuff coming in is introduced correctly, that is correct on the incoming point. Then once you have encoded types, you're going to be transforming them into other types. So for instance, you might bring them in with the database types and then transform them into that document view or transform them into the row view. The idea is that you can do these transformations without having to check for more boundary conditions, right? Like you don't have to then double check, well, I have a product. Is it really a product? Do I really have that? Does it really have these fields? That's all encoded in the type layer. Okay, so let's go ahead and look at a first type that might help us with this. So what I have here is a type that I'm creating called fixed text. So your arbitrary string type is generally some large character set, and then it's infinitely long, right? Or at least pseudo-infinitely long. But lots and lots of records, you actually want to control or constrain how many characters it can be and what class of characters you can have. So what I'm going to do is create a type called fixed text. That type is going to have a max, that's a natural, a min, that's a natural, and a regular expression that defines the algebra. Does everybody here know what a regular expression is? Raise your hand if you don't, and I'll go into it. Okay, so good. Yeah, so using the max, min, and regular expression, now I can create a character class and a length to more specifically define a given piece of text. What you should notice here is these are actually in the types. So these are not like if-then things at the value level. This is actually saying that this type can only have however many characters I type here and can only have these expressions. So here's our first smart constructor. Whenever I defined this one screen ago, I have all these rules, but in order to actually enforce them, I have to create in Haskell what's known as a smart constructor. This one's going to be called fixed text from string. And what it's going to do is take a string and produce either our fixed text with a given max, min, and regular expression or character class, or an error. All right, so going through this code just a little bit, it's a bit hairy code, but basically what this is doing is grabbing from the type level the maximum value of your character class, the maximum length, and this one's grabbing the minimum length. So then if it's too little, then that's going to be rejected right here. If it doesn't match the regular expression, it's rejected here. Otherwise, we're all good to go. And it goes ahead and produces it, constructs it. So then once this is done, you have your correct fixed text. And as long as you guarantee that your code only uses these smart constructors, you know that you have a correct construction and that it meets those properties. You have that minimum, maximum, and character class. And what's nice is if you have two different fixed texts and they have different minimums and maximums, they're not equal to each other. So they're actually prohibited from taking each other's place. Here's a few examples. A fixed text 31 all alphanumeric is created. Example text 1, 2, 3, 4 is a string that's ran through our smart constructor and outputs the fixed text type correctly. That's why we have a right instead of a left. Again, we have a 10, 1, and again alphanumeric, and this one is also correct. Lastly, I have a fixed text 31, and it expects all digits, but the input isn't all digits. So instead we get an error, left fixed text error on regular expression. So the thing to see here is that this fixed text and this one are not actually the same type, even though we use the same type constructors, because of the values that we've put in. This one now expects one that's 31 in alphanumeric, while this one is 10-1 in alphanumeric. So you can't use them interchangeably, and that's what you want. You want your types to contain information about where your code is usable. Everybody good so far? Sure, yeah. So in Haskell, there's a type called either. The left side of either is generally used for errors, and the right side is used for correct values. That's a good question. Yeah, so I'm kind of jumping in and assuming a lot of Haskell. I think if you guys don't know something like that, like please just stop me and I'll go through and explain it. But I really wanted to talk about, we've had a lot of talks where they're introducing a language, and I really wanted to get into something where you can see like why you might want to bother learning one of these languages that have all these neat little features. And to do that, I sort of have to jump. I can't start and say these are all the things that are Haskell, but I'll be glad to stop and kind of go over it, anything. Okay, so those were properties by construction, right? So now what we're going to talk about is more of a property of what you can do with it. So monoid is a word that you hear a lot. If you're into Haskell or Scala, you'll hear monoid talked about a lot. It's a scary word. All it means is it has an associativity and a null member or an empty member. So what we're doing here is defining our fixed text to be a monoid. Well, the first thing you can tell if you're going to make something a monoid and you know it has to have an empty member, probably your minimum can't be anything besides 0. Or at least that's the way I felt about it. So I made my minimum as 0. So any fixed text that's a monoid has to have a minimum of 0. And then here's our append. In Haskell, you always get these things where they have like mempty instead of empty and mappend instead of append. And that's just a artifact of the language. You'll see it with like fmap too, instead of map. But basically, we're defining an associativity operator, and it's just string concat. So it's going to take your string and another string and can combine them together. So let me back up here. One thing to note, I'm taking in a fixed text and another fixed text whose types have to match, and I'm returning a fixed text whose type has to match. So what does that tell me? It says that I don't know a lot about what's going on in the function. That's how I read that. If I see fixed text, arrow fixed text, arrow fixed text, I mean, other than the fact that I have the same thing, sort of, that I got in, I don't really know much about what's going on. And that's when you're going to start seeing stuff like QuickCheck. So the first thing you have to do in order to use QuickCheck is define something as arbitrary. What QuickCheck allows you to do is put in some random generated values and then check some property of a type. So what we're going to do is create what you need in order to get those random generated values. So here we have, in order to create what we need, we create what's called an arbitrary. And basically, you're just saying, here's how you generate a fixed check at random that looks like this, that has some maximum value, some character class, and then has a 0 character minimum. And so I kind of want to skip over a little bit of this, but basically it's generating a random fixed text value. You just sort of take my word for it. That's what it's doing. The code's a bit complicated, but if you have a question about it, just hit me up on Slack or after this. But it's generating a random one of those. Then finally, we can do we have a property test. So now that I have random ones, I can ensure that that code will actually, that type will obey the property of monoids. The first property of monoid is it has an empty member, and that empty member obeys this law. That is, the empty member concatenated with a regular member is equivalent to just that regular member. So if you think about addition, 0 plus 1 is 1, right? Or 1 plus 0 is 1. So here you have 0 plus 1, 1 plus 0, and they're the same. Okay? So we want to test those. And then the last thing we want to test is our associativity. And so that says that saying 1 plus 2 plus 3 is the same as saying 1 plus 2 plus 3 are the same. And that's what this is saying right here. You can see the parentheses kind of roll it out. So to try this out, I made up a fixed text. My fixed text has a maximum of 10 and all these different characters that I put in just to make it somewhat complicated. And then here's my left ID test. So I have my empty one against some random one that's going to be generated for me by QuickCheck is equal to just that random one. On the right, I have some random one concatenated with my empty one is again equal to just that random one. The bool obviously giving me a true or false of whether that property holds. Associativity monoid. I have example fixed text, example fixed text, example fixed text. Well, that's really useful. So down here is a little more information. Left associativity. I have some string, again, generated by QuickCheck, some other string generated by QuickCheck, concatenated together, and then concatenated with the third one. And then with the right associativity, I have some string concatenated with two others. So now we have properties that can be tested against, and then when you run QuickCheck, it runs through and says, oh, look, they all work. Hooray. I can write a monoid instance. Any questions so far? Awesome. Okay. So earlier I had a document view and a table view, and then had a normalized database view. So here's what those might look like in the types. You might have a product, a customer address, and some states, right? So you enumerated type. And then here, these are all fixed texts that I made to define our different character classes more carefully. Notice that nothing in here is like a primitive type. Like I don't have something called int or something called string. That's a really important property in using types to transform data correctly, is you want to keep your primitives very isolated. That way you have more rich information about what's going on. And that'll really help the compiler tell you what's happening with your code. I think a lot of the time when people come from other languages, especially, at least for me, C, you have a lot of int, you have a lot of char star, you have a lot of void star, and like those types are very useful for the compiler and very useful for the compiler in terms of performance, but not very useful for you in terms of understanding what's happening in your code. Getting used to adding more layers of types is how types become magical, and it's how you switch from the types being how you check your code to actually how you design your code, right? So like when I would design something like this, I'd have this product, and if you notice, it's a nested product, right? It has a customer inside of it, and a product name and a product number, and each one of those is a nested field in itself. So then, putting them all together in that nest, like I said, you'd have some product document. And then if I wanted to do that first document view, I would probably have grab one of these. But if I wanted to do that table view, what I'd do is I'd split all those fields out, and I'd have a product number, product name, product version. All these different fields are now flat. So that gives you a really obvious function. You're going to have some function that takes this, a product document, and transforms it into this, a product row. So what you can look at that and know things about what it's doing. And that's the idea. You want to be able to know things about what it's doing. You want the properties encoded in the type system. So by making this product document transform into this product row, if I miss a field, if something isn't there, then this won't work. This is a property of isomorphism. It says you can take one representation of a thing, transform it into some other representation of the thing, and go back without losing any information. It's a really nice property. and why functional programmers threw a bit of a hissy fit when JavaScript people started talking about isomorphic server code. Because it's just a really important thing for functional programming and immutable programming in general. But people just need to calm down. So toProduct row is exactly the function that I talked about earlier. We start with a product and we get to a product row. So here's how I would write that. This dot dot means that it would, it's going to take all the field names and just automatically bind the values to the field names. That way I can write a nice terse function, product row, product number, product name, version, product description, just listing out all the fields. So here I have a product, and I grabbed the internal members of that product. Let me back up a couple slides just to remind you. So a product had a customer and a version and a name and a number. And here I'm grabbing that customer out so I can get the fields there. And I'm grabbing the customer's address out from customer. And then I'm flattening it all out right here. Okay, and then if I had a product row and I wanted to go backwards, I just got to do it all in reverse. So now I'm constructing a customer and I'm constructing an address to build a product. All right, so if I miss one of those fields, either direction, the compiler is going to tell me about it. Not only is it going to tell me about it, because I've named all my types well, it's not just going to say error missing int. It's going to say error missing product name or error missing product description. That's really nice. And when you get that level of granularity, that's when you really start switching from you're using the types to check your code to using the types to design your code. Again, I have to do more arbitrary generation so that later on I can use QuickCheck. So James Haver and Sungke Han wrote a package to actually generate arbitraries automatically in Haskell. So I'm using that, and it's called ADT arbitrary, I think. But I'm just showing you don't have to have those big long arbitraries every single time. Usually you can make something that looks like this. It's nice and short. Still a little bit more boilerplatey than maybe I'd like, but it's pretty good. So, all right, so now most code is mutable. The other way that I like to use QuickCheck, whenever you write a program and you have all your beautiful types and they're all working really well together and you think you've done everything right, and then somebody goes through and they change something and they just put an empty string in or they do some other ridiculous thing, you want your tests to tell you about that. In other words, you want your tests to check your types, which seems really weird, but I mean, in production, that's what you want. So here we have a test. It's an ISO test. It's checking that isomorphism property. It's making sure, so here, because it's part of the type signature, we know that products have to get to product rows. That's only one part of isomorphism. It's not just that products create product rows, it's that it creates the same product row with the same information. And that's what we're really checking here, is to make sure that that information isn't destroyed. So the first was to check that the structure and the skeleton of the thing is correct. Here, the QuickCheck is actually going to make sure that the information on the inside is correct. So basically, it's going to generate some random product. It's then going to transform it to a product row, and then it's going to transform it back from a product row to a product, and then check to make sure that it's equal to the original product. And it did it 100 times, and 100 times it worked. Hooray, we know for sure it all works. We've done it 100 times. What could go wrong? Once you get to 100, everything works. That's the rule. Okay, so I was being a bit facetious there because there have been plenty of times that QuickCheck hasn't caught errors that I've made, right? Like, I'm very creative at making errors, and I thwart QuickCheck regularly. So I'm very interested in ways to help check that data layer, that layer right below types. There are several languages that do that automatically. Some do it by trying to encode more of the value layer into your types. So you'll see stuff like Agda or Coke or Idris. That's what they do. Then there's another system which tries to take existing languages like Haskell that already have rich type systems and add a layer of refinement to them. In fact, those are called refinement type systems. Liquid types is one such system. So here I have a little bit of liquid type code. The first note here is it's proofs, not tests. In other words, if something is true in a refinement type system, it has to be true. It's not just an arbitrary set of data that make it true. It has to be true all the time. The way that at least the liquid types refinement system works is it uses a thing called Z3. Has anybody heard of Z3? Okay, cool. Yeah, so it's an automated theorem prover. It'll actually generate test cases and try and invalidate some code that you've made. And here's an example of how you get to use it with Liquid Haskell, which is much nicer than using it on its own. We have some list of data A, and then we actually are running look, it's just Haskell, but we're running it here in the type level, or sort of the pseudo type level. And it's saying that all of the values here have to be not empty. So some list here has to be not empty in order to count as a not empty list. If I try to use it unsafely, it doesn't work. So I actually want to just now show a couple of examples. So the first thing I want to show is using that. So I'm going to have to try and put this down. I hope it works, but I need both hands. All right. Don't fall. Oh, I knew it. There we go. Okay. So probably that needs to be bigger. That look good? Look about the right size? Yeah. So let me go down to the one that I just showed you, right? So here we have not empty list, which is some list, and it has to be not empty. So what does it mean to be not empty? It means that if it's empty, then it's not empty. Otherwise, it's fine. So let me try and run it. So to run it, so there's some really fancy ways of running Liquid Haskell inside of your development environment. I'm not going to use any of them. So Liquid, I just call Liquid and then I call it on the file. So Liquid internal. And you see it result is, look, it tried to figure it out, everything worked, and we're good. Everything's safe. Now I can show you here, I'm going to try and use it unsafely. So I'll uncomment this, save it. Oh my goodness, what was I thinking? Don't do that. And I get this nice big error. And it says that this function is trying specifically to break my own rule. Why would I want to do that? And so what you're seeing here is the kind of thing you used to only be able to catch at either runtime or in test time, actually being caught in compile time. And that's what's really nice. And that, again, that's provably correct. So that's not the same thing as what QuickCheck would do, which would be try a whole bunch of instances. It's actually proving that this has to be this has to be true or false. And it'll tell you if it can't make that proof, it'll tell you, and it'll say, hey, you have to try and do a couple things to fix this so I can actually say something intelligible about it. Or you have to give it an escape hatch if you have a couple things that it can't say anything about. So that's one example. I kind of wanted to mess up some of the code that I showed earlier, and I wrote all the examples here. So if you ever want to, I'll put them on GitHub so you can see them. But this is all the stuff that I wrote. But I also wanted to show that like the way things get transformed. So here we have toProductRow. Let me add a little REPL here. It's not as fancy as the Erlang REPL that we saw last time, all way back in November, but it's a pretty good REPL. Okay, so everything's good. I don't have any warnings. But let's say, because I am silly, I left off the row description. Okay? Oh, look. It can't match. The actual type is t-text to product. So that tells me that that was missing. There's another way of actually defining types in Haskell. Let me kind of show that really fast. So that's going to be row product number, row name, row version. Oops, I'm doing that wrong. That's silly of me. Isn't this exciting? Everybody watch me code. But I really wanted to show, like that this isn't, you know, hard to do. I mean, like, it's just like the compilers and the tools are there to help you get it done. Version, row version, customer, and lastly, row description. Okay, so I didn't miss anything. Good job. Go me. I like it. Oh, define but not used example product. See, so I'm not using my value. Yay, compiler, thank you. Okay, so I'll take that away and type example product here. All right, now I'm all good. Okay, so what I wanted to show is, so this was a different way of defining everything. And let me line everything up so I don't lose my mind. Sorry, I have very... Oops. There we go. Okay, so you can kind of see what I'm doing here. Does everybody see what I'm doing here? I'm just saying that this is the product number, this is the name, this is the version, this is the customer, this is the description. But now, let's say I left off at one of these internal fields, so product customer. So I get here, I get an error that says, in the equation here, field missing product customer. So it actually tells me what's missing. So then I know, oh, well, don't do that. So that's what I meant by it kind of determining the structure for you. And then let me see, what are some other neat things to show? Let me show you some of the fixed text stuff that I was talking about earlier. Okay. So this is all the stuff you need to make a different fixed text, and kind of in more detail, here are some examples. But you can actually make these. You can actually make them right here. So I guess one thing I wanted to show is. There's nowhere I need to define what a fixed text is other than right in the type. So 220 and then alphanumeric is the definition of a fixed text. And that was accomplished by careful construction of this guy here. But I guess I got a little bit of time, so maybe I'll go into this just a little bit more detail. So in Haskell, there's a way of going from the type level to the value level. The value level is what you normally are programming in, and then the type level is sort of the language that's about that level. It's called proxy. And so here I have this value max, and that exists at the type level. If I want to grab something out of it, what I do is I say, by proxy, I want some sort of max, and then I can grab that value out of it like this, and that gives me one of those maxes. So that's how it's, so in instance, if this were fixed text 3, then it would know that by proxy that means I need a 3, and that's what I'm checking against. So then another thing that I like to do is I like to have all of my errors actually encoded and not just use a string or a text. So I could just have like error text and like you can just write whatever you want, but actually I like to make all my errors typed as well. So fixed text error min, fixed text error max, and then this might look like it's string, but really what it's doing is saying what string you had that was good and what was the actual string contained. And actually that'd be something we could fix up. That it would be better if that were a little bit more descriptive. So instead of saying just fixed text error, regex string, trim string, maybe it would be better if I wrapped those so that they were a little clearer as to what they were. So new type. The nice thing about new type is it doesn't cost you anything at at runtime. New types are actually erased at runtime. Erased means, so, well, I guess I should ask, does anybody not know what erased in a type system means? Okay, good. I was gonna be so impressed, because this stuff I just learned really recently. So yeah, in some of the types that you see, they have an existence that only is until it's compiled. And then at the compiled point, that type disappears. So when you're running it, that type is gone. Other types continue to exist past that point. So the types that don't exist are called erased. They're erased types. The types that do exist aren't erased. Does that make sense? Okay. Is there something like that in Scala, isn't there? Yeah, I think that's pretty. Yeah, I think in Scala, it's harder to do the opposite. It's harder to not get type erasure than in Haskell. You can declare something typable or declare something data and get that type information explicitly. That's actually, I think, what makes it hard in Java, if I remember, like doing that conversion from Haskell to Java. But that's getting outside of what I know, so I probably shouldn't.
How does the compiler know that you're erasing it? Or is it inferring to that?
So what the compiler knows is that this function, what the compiler knows is that a function can't have an empty array. So for instance, if I write a function that adds 1 to a natural number, then you can prove that that number can't be 0. So it's stuff like that. So it knows that you can't represent certain states. It doesn't, you can write functions where it doesn't know whether it's empty. You can definitely write functions where it doesn't know whether it's empty. And then you either have to give it an escape hatch saying, never mind, don't worry about it. Or you have to give it more information so that it can then know that that's not empty. Does that answer? Yeah. Okay, awesome. Yeah, so I mean, that's like one of the things that's sort of like, when people talk about stuff like Agda or Idris, they sort of have a bad habit of making it sound mystical. But it's really just the compiler just it'll only let you do what it knows for sure is okay. It'll only let that stuff through. And if it doesn't know for sure something's okay, it'll stop and make you actually put that in. And Haskell works the same way. It's not as crazy as those languages, but you know, it will only let you do what it knows is okay. So if it can't prove that when I change a product to a product row, I get a product row, if it can't know that for sure, it won't let me do it, right? Or at least throw a warning at me, right? So that's what we saw earlier. Let me go back there really fast. That's what we saw here. It threw a warning at me. So it said, I don't understand why you're trying to construct a product row to a product where you don't have all the fields initialized, but maybe you know what you're doing. And you can actually turn that feature off because I never know what I'm doing. So I always want to assume I don't. And then we're on the same page. Me not knowing and it knowing I don't know. So, but yeah, that's exactly what's happening here, right? So like here it knows that I've gone from product row to a product. It can prove that I made that transformation. Here it says, okay, you've sort of gone from a product row to a product. You have the constructors, you have everything you need, but you're missing some data. And so it just gives me a little warning. It says, hey, you're missing some data. And like I said, you could turn that into an actual error. And in other languages, I think that's always an error. In pure script, that's always an error, isn't it? I believe so. I think it is. But it should be. I wish it were always an error. Like I said, I turn on a feature that makes it so that it's always an error. But yeah, so like this is, if I want to make like a regex, so I'm just going to make a very simple example here of using a new type to wrap something so I get a little bit more information about it, since that was like one of the things I said we should do. So regex string. Okay, so look, now it's gonna kind of guide me. So I changed the type from string to regex string. So it says, hey, wait a minute, that doesn't work. This is wrong. Oh, well, first of all, I gotta learn what I'm doing. So that's the first thing it's telling me is you're an idiot. Okay, there we go. Now what it's saying is there's no instance for show on regex string. So So show is how Haskell knows how to display something, so I'll add that. Well, there's no instance for equal, so I'll add that. No instance for OR, so I'll add that. And now it says, hey, I can't match string with regex string. I'm going really fast, I'm sorry. Down here it's saying this stuff. And when I click enter on it, it takes me to where it has that error. And so what this error is saying is fixed text error regex. And so the error is actually happening right here. And it's because this type used to be regex. It used to just be string. And now I've changed it to regex string. So to fix it, I have to actually put a type wrapper around regex string. But I'm not going to do it right here. I want to do it up here where I'm constructing a regex string instead. And so now I have this regex string constructed, but I'm getting a different error, and it says couldn't match regex string with car again. And when I hit enter on this one, it shows me a different error. And what it's doing is it's comparing two different strings, the trim string, which came from something else, with this regex string. So I'm going to unconstruct it here. And then that gives me that error fixed. And you just sort of keep going through and doing this stuff until it all works out. And just letting the compiler guide you. And getting close. Oh. All right, unregex. All right, all my errors are completed. So now it compiles, now I have what I had, but with more information, right? So now, like, when I go and I look at my error types, it's not so confusing. I have a fixed error regex. The first one was the regex string that was erroring against, and the second is the string. I could do the same thing and have another one where it's like input string, right? And I could rename this as input string. And that wouldn't be a bad thing to do. I don't want to do it in front of you guys. You already watched me code enough, so. But hopefully that gives you an idea of how you can use properties and types in order to encode those properties. What I really want to get through is a lot of times when people talk about property testing, they're doing a lot of talking about QuickCheck. What I wanted to say was all of typed programming is about properties, not just the QuickCheck part. In fact, QuickCheck is your last line of defense. You want to do as much as you can with the types to get all those properties encoded. And QuickCheck is for those properties that you can't encode in the types for some reason, either because it's very inconvenient. For instance, if you're using a lot of imported functions, or because the nature of the problem is inherently dynamic or is inherently about transformation in the same type. A good example of that is like transforming lists or sorting lists. Like you're always going to want the same type in and out, so you're going to want something like QuickCheck to do that. I think.
So do you find that doing property-based testing reduces the need to do like unit testing, or does it automate it, or how do those play together?
Yeah, that's a really good question. So in my company, we don't write very many unit tests at all. So first of all, I think really it's types that really help reduce unit tests more than anything else. Property-based testing, it's such an unusual category of tests. It's somewhere in between unit tests and integration tests, somewhere around there. But the tests that I generally write the most in Haskell are serialization tests. So things that I think of as being on this. I talked about there being a boundary layer here, and let me go back to that really fast. Yeah, now that I've gone through everything, like I said, at the boundaries we use smart constructors and QuickCheck. So that's really where my tests live. So when things are coming in from databases, coming in from serialization or in from services, I want to make sure that I have that specification tight, so that once I get it into types, I know that everything's correct. So that's like my main use of QuickCheck, is to run serialization tests. So I make sure that I can serialize to some representation, come back from it, and get the same value back. Yeah, I think that's stuff like that is where QuickCheck really comes in handy. And then again, the other thing is, if you define all your arbitrary instances, if you get used to working with types all the time, and you define your arbitrary instances ahead of time, you can actually use QuickCheck as a form of TDD. So you can be creating generated values and then seeing how your functions work with those values as you go along. So you can sort of think of it as like types and tests design working together. And I also wanted to show a little bit of working with types in the REPL, and that's why I did that, just to show that it's quick. It's not compile and wait. I mean, sometimes it's compile and wait, but if you're careful, you can usually get around that. Usually it feels quick. It doesn't feel crazy. I think that's really all I had. One thing I wanted to say was, my company, Plow Technologies, our entire backend infrastructure is in Haskell. We write embedded Haskell code. We also have Haskell on the front end. Kevin wrote a really, really nice Haskell framework for GHC.js, which is a JavaScript compiler. And we're always looking for good people. So if anyone's interested in, writing Haskell professionally, just hit me up, send me a resume, whatever. Thanks.
All right, thanks, Scott. That was awesome. Good work. Next month, we're going to have Dylan Forsha, back in the back there, that's going to talk to us about doing functional I/O. So he's been kind of sharing some ideas he's got around that. That's going to be a pretty interesting talk coming up. And once again, if you want to contribute, just come and find me. We can talk later. So thanks for coming, guys. Have a good one.